Thank you very much. Now we have Andre and David, who's going to talk about testing for finite state machines.
Yes. Okay. As you all have heard, my name is David Anthony Fields, and this is Andrés Garced, and we'll be talking to you today about automatic invariant testing for finite state machines. This is joint work with Sophia Turano and Marco Morazan from Seton Hall University. A modern trend in teaching formal languages in automata theory follows a programming-based methodology. One approach to following this trend uses FSM, a domain-specific language embedded in Racket. It allows students to design, implement, validate, and verify the machines that any student may encounter in a typical flat course. Tightly coupled with FSM is a book, problem-based formal languages in automata theory, where students are introduced to the design recipe for state machines. And following this design recipe, students then develop state invariant predicates for each state, and they have to design, implement, and validate these invariant predicates. While designing and implementing these invariant predicates may be straightforward to students, how are they supposed to test them? Should these tests solely rely around the implementation of the invariant predicate? And if you're thinking, yes, I'm sorry, but you're sadly mistaken, because the invariant predicates have to rely on the transition relation that they develop. And by that, I mean they have to test all the paths that lead to the state that they're developing the invariant predicate for. Now, this is an MP problem, and I would like you to consider the following example. Consider the number of possible paths without repeating a state in a complete graph of n nodes. The number of paths of length 2 is n times n minus 1, and the number of paths for length 3 is n times n minus 1 times n minus 2. So we can see that the number of paths for length n would then be n factorial. And if we wanted to find the total number of paths for the entire machine, we'd have to sum up all of these n factorials. So I think we can all agree that asking students to write this many tests is just unreasonable. So today we'll be presenting a tool that automatically tests all invariant predicates by traversing a transition relation that students develop to provide a thorough test suite for their invariant predicates. So before I get into the implementation, we should first highlight how we FSM and how students are then able to program within it. So we'll look at a DFA for the language where all words contain the pattern A, A, B, A, B, and the design idea for this machine is that each state will contain a different progression of the pattern. For example, the starting state will have none of the pattern being detected, and the final state will have the pattern A, A, B, A, B be detected. So here we can see the implementation of this DFA, where at the top we have the state documentation. This is where the students would informally define their invariant predicates. In the middle, we have the implementation of the machine itself, where the arguments are as follows: the set of states, the input alphabet, the starting state, the set of final states, and then the transition relation. And in the case of a DFA, this has to be a transition function. And at the bottom, we have the unit test for this machine. For this to be a thorough suite, students must include words that are both in and not in the language. And finally, we have the transition diagram of this machine at the top, where the starting state is highlighted in green, the final state is double circled, and all edges in the transition diagram correlate to one of the transitions found within the relation. So assuming that all of these tests pass, the students can then move on to formalizing their invariant predicates, where they would then take these invariant predicates from the state documentation and then turn them into code. So for the sake of brevity, I'll only show one of them. So we have the invariant predicate for A, and the purpose of this is to determine if the consumed input only ends with a single A and doesn't contain any other prefix of the pattern. So here we have the test for the invariant predicate, and I want to draw your attention to the first line, check invariant holds, as this is the problem that we're going over today, or we're addressing today. So here we have the first test in this suite, A, which tests the edge from S to A, and the second test will test all of the edges highlighted in yellow. So I now have a question for you guys. Do you think this is a thorough test suite for this invariant predicate? Yes. You would be right. The answer is no, as all of these all of these edges highlighted in blue are also words that can be correlated and used to test this invariant predicate. So as I've mentioned earlier, to thoroughly test an invariant predicate, we have to rely on the transition relation that the students develop. And for any of you guys curious, the number of tests that the students will have to write for this machine in particular would be 50. So now to circle back to the implementation of our tool, we wanted to find all words that use a transition rule at most k times. So our implementation can be divided into 3 main phases. Phase 1 is the machine refactoring, where we remove all dead states. Phase 2 is the computation generation, where we would accumulate all paths from any accepting computation. And finally, we would then go and test the invariant predicates after using the paths that we then generate. So for phase 1, this one is pretty simple. We just take any states that don't transition to or they don't have a path to a final state. So if we look at this machine here, we can see that this state ds does not lead to any final states. So we can simply just cut it off in all of its transitions without changing the language of the machine, and then we can then take this machine and then move on to phase 2, where we then generate a test suite using the refactored machine by doing a breadth first traversal of the transition relation. So in doing this traversal, we accumulate 2 values, the queue of computations to explore and the list of computations found. So now I'll run you through a quick example using the machine that we just refactored, where our starting queue is all of the rules that are usable from our starting state. So that would be SBB and SAA. And then we can take the first of the queue, add it to our computations found, and then we can then extend this rule SBB with another applicable rule, BAB. We can then do the same for SAA, add it to the computations found, and then extend it with ABA. And then in a similar manner, we can do the same process for the remaining 2 rules. And then now that our queue is empty, which we see here, and we have all of our computations, we can then move on to phase 3, where we then go to the invariant testing. So we take all of these paths and then associate them with their correlated state, and then we test each invariant predicate using the rules that we have here. Now this tool should return a list, and this is a list of pairs. If the invariant holds, then this will return an empty list, and if any of the invariants fail, it will then return a pair where it'll have the state and the corresponding word that the invariant does not hold for.
So now that we've discussed the design and implementation of the tool, we can discuss the practicality of this tool in a flat classroom. So thoroughly testing machines like this is computationally very difficult, and thus we need to determine whether it's actually feasible for students to use this tool in a flat classroom. And if it is, what defaults, for example, the maximum number of times a rule can be applied should be. In order to determine this, we ran an empirical study on the various machines that we collected from different flat textbooks to determine if the tool would be able to run in a feasible amount of time on those machines. There were 17 in total, and you can see the characteristics of these machines on this table here. So we have the number of states, the number of transition rules, and the number of the type of machine, how many transitions are coming in and out of the dead state. And here we can see that these machines are all fairly small, containing 10 or less states, because these were found in introductory flat textbooks. However, some of them are still somewhat complex, containing 20 plus, 30 plus, even 40 transition rules. So in order to determine what the default number of maximum rule applications should be, and also whether or not this tool refactoring the machines was a feasible optimization strategy, we collected the number of rules needed to thoroughly test the machine, and we denoted between whether the machine was refactored and not refactored, and whether we only used a rule at most once or at most twice. And so here we can see that for when the machines actually did have a dead state that could be removed, the number of test cases is reduced significantly. And so it does make sense, it appears that it does make sense to include this optimization for the tool. Another thing to note is that some of these examples are actually infeasible, and when it's denoted as infeasible, it means that the laptop actually ran out of memory. And so because there are so many examples, test cases being generated, because we're starting to hit up against the wall of NP, the laptops just simply do not have enough memory to compute these examples. And thus, it's because of there being so many unfeasible test exam machines for when the maximum number of rule applications is 2, we have decided to set the default to 1. However, we've included a keyword argument so that students are able to increase it at their will. So now that we've determined that it is practical to include these, to use this tool on typical examples found in flat textbooks, we wanted to see what the runtime characteristics would look like. And so we ran an average of, we took the average of 50 experiments across all those machines on the laptop provided to students at our institution, so Lenovo X1 Yoga. And we had 2 of them. One of them was running Windows and the other was running Linux. These are the results for when there was only 1 rule application allowed. And here we can see that for all the machines aside from machine 15, the runtime was under a second. And so we feel that, at least for using the rules at most once, that it is most definitely practical for students to use this tool in the classroom. Interesting to note is that when there are no dead states to be removed while we're refactoring, the performance hit is quite large. And thus, we also made the optimization of refactoring the machines to be a keyword argument, with the default being that it does not, so that way students don't incur this performance hit unless they actually need it. These are the results for when we allowed rules to be used at most twice. And here we can see some of these unfeasible examples popping up again. And what's interesting to note is that there's some examples that will run on Linux, as we can see here, but however, will often run out of memory on Windows. And one reason we suspect this might be the case is that the out-of-memory killer is killing processes on Linux, which is something we actually observed occurring on the laptop, and thus was making more memory for use for the tool that wasn't occurring on Windows. Now that we've talked about the tool, we can actually see it being run. So here we have a student-submitted design for the DFA that we looked at previously. And if we look at the transition diagram, the keen eye among you might notice that this contains a bug and is different from the one you saw on the slides previously. So if we test it using a variety of different invariants, oh goodness. We can see that there are 2 invariants that do not hold, the invariants for S and the invariant for A. And so if we take the word that breaks the invariant for A at the bottom and run that in a dynamic visualization for the execution of the machine, we continue stepping through, we can see that the machine rejects when the transition is coming out of D. And so if we look at the state documentation for this machine, we can see that the largest prefix in this case is AA, and thus shouldn't actually be going to A, but rather should be going to B. And thus perhaps a student made a typo somewhere along the way. And if we actually fix that mistake such that it follows the state documentation that the student wrote before, we can see that now all the invariants hold. So now that we've talked about the tool that we've implemented, Let's talk about how some other people have implemented tools to test machines. So JFlap and Automata Tutor, Automata Simulator are tools that allow students to implement machines and test them. However, in contrast to FSM, they do not provide support for testing invariants. Automata Tutor is another tool that provides predefined problems for students to solve. In contrast to FSM, that doesn't allow for the definition of arbitrary machines, and it also doesn't provide support for testing invariants. Proof Checker is yet another tool that allows students to test machines and does provide support for testing invariants. However, the way that it does so is by the generation of random words and thus doesn't provide nearly as thorough test coverage as a tool being presented today does. So, to conclude, today we have presented a novel tool to test invariants in machines via the use of traversing all possible transitions, and does so by single expression and allows the programmer to debug their design and have much more confidence in the design before they actually attempt to verify it. For future work, we would like to use this software as the basis to start generating test cases using Quick Check for those examples in which it's unfeasible to use this tool. We'd also like to extend this to work with pushdown automata, and we'd like to determine the effectiveness through the use of human factor studies.
Thank you very much. Any questions?
Thanks for the talk. Is there a specific reason why you chose like a testing approach over like a full-fledged verification approach? Because for finite state machines, it should be doable in principle.
I think it's mostly for the ease of proof. So we find that the actual proof, proving that the logical equivalence between the language of the machine you've designed and the language that you're designing for is much easier to write if you do it through the use of invariants. And so I guess it's more just an ease of difficulty.
Okay.
Yeah, I guess I have a related question, which is, what is the actual expressiveness that you need from those invariant predicates? Right, so it looked like you had kind of arbitrary functions as the predicates, but it could be the case that if you didn't really need them to be arbitrary predicates, you could express them in a DSL, then verification could potentially be much more practical.
I could see that being the case. It could be something that we could look into in the future for sure.
Sorry, I want to repeat the first question because I didn't really understand the answer, right? Like these are all highly decidable systems. So you could still have people write the property-based testing predicates, but you can actually just test the predicates directly. You can just, these are decidable. Like why do you need to do any unit testing at all? Those are not, it felt like your answer was you wanted people to be able to write the properties, which is fine, but you still don't have to test it using property-based testing. I think that was your question, yeah.
So
everything here is brutally decidable.
Yes. I mean, I think part of it is that this is one of the first times, aside from an introductory like discrete mathematics course, that the students at our institution are getting into like verifying programs, and thus it's easier for us to transition them into verifying things when we can kind of transition them through the use of invariant predicates. I think perhaps if we had more experience, if the students had more experience in actually verifying programs in that way, that maybe we would be able to do it like that, yes.
Okay. My follow-up, separate question is, you said you wanted to do user studies. I want to know what the user studies are. What do you want to study?
I think some of the research questions we'd like to examine in the user studies would probably be whether the students felt that it was helping them in debugging their designs, if they felt that it was straightforward to use, and if I think those would be the two main points really. If they felt that it was straightforward to use, if there was any, I guess, like UX issues with the interface of them actually using it, and if it felt it was actually helpful for them to actually like have more confidence before they go and verify their design.
Thank you very much.